So we've seen what entanglement swapping amounts to, and now the question is, what do we make of it? I want to start out by emphasizing that there are some analogies with classical situations here, and that may or may not give us some insight. So I've written out the initial state here, left off the term that makes it length 1, and I've colored it in a way that lets us see Alice's qubit and Dave's, and Bob's and Carol's. And we can already notice some correlations here that aren't the correlations that we were initially interested in. Suppose that Bob and Carol each measure in the computational basis. You can think of that as measuring z-spin. Let's go back and look at the picture. Here's Bob, here's Carol. Here they are before. They never were correlated to begin with. Bob isn't correlated with Carol. Alice isn't correlated with Dave. But there are some cross correlations here. If Bob and Carol each measure z-spin, they're going to get the same results as Alice and Dave do in that order. Just look here. Suppose, for example, that Bob gets 0 and Carol gets 1. Then Alice will get 0 and Dave will get 1. If Bob gets 1 and Carol gets 0, Alice will get 1 and Dave will get 0. So there's some extra correlations in here. And as we'll see, correlations like this could be classical. Now go back to our original entanglement swapping example. Alice and Carol aren't entangled. Bob and Dave aren't entangled. Alice and Carol perform an entangling measurement. Bob and Dave end up entangled. Let's now think about the relationship between the pair that Alice and Carol possess and the pair that Bob and Dave possess. Initially, Alice and Carol aren't correlated with one another. Bob and Dave aren't correlated with one another. Or to put it another way, they aren't entangled with one another. Alice and Carol aren't entangled. Bob and Dave aren't entangled. But the pair of particles that Alice and Carol possess, that pair is a system in its own right. And that system is entangled with the pair that Bob and Dave possess. That's a system in its own right. And in fact, that's exactly why entanglement swapping works. It's because of the entanglement between the Alice-Carol pair and the Bob and Dave pair. And that means that in a certain sense, there really isn't anything here that's so very different from what happens when you just have a pair of entangled systems in general. We know that when you have a pair of entangled systems and you make a measurement on one, that will have consequences for the other, depending on what you measure and what the result of that measurement was. We can also see that there are some classical cases that have some analogies, though very imperfect ones, to entanglement swapping, or to the kinds of correlations we've seen here. Suppose Alice and Bob have a pair of classically correlated, we'll call them coins, although you could use another example. So in other words, if Alice flips her coin and Bob flips his coin, these coins are created in a way that guarantees the results will be the same. They'll either both get heads or both get tails. If you don't like coins as an example, you can think of electronic gadgets. You can imagine how this would work. And likewise, Carol and Dave have a similar pair. Well, Alice and Carol aren't correlated. Alice and Bob are. And Bob and Dave aren't correlated. Rather, Carol and Dave are. But because of the correlations that we do have here, if Alice and Carol each flip their coins, the product of the results, +1 times -1, whatever it may be, will be the same as the product that Bob and Dave get when they flip their coins. So that's kind of like a classical analog of the fact that the Alice-Bob correlation, together with the Carol-Dave correlation, gives us a correlation between the Alice-Carol pair and the Bob-Dave pair. It's not quantum, but it's similar. But nonetheless, you may be impressed by the differences. I mean, you may think that quantum entanglement is importantly different enough that there's something extra going on here, and I wouldn't disagree for a minute. The question is just how do we think about this extra? And here's the point. Entanglement is essentially a matter of correlations. Entanglement isn't something that you can recognize in one shot by itself. So suppose that we have a pair of qubits. And the question that we're asking is, are these two qubits entangled? Here's the thing. Nothing you could do by way of measuring those two qubits would tell you whether or not they are entangled. Even if they, quote, really are entangled, you can't tell that. Any experimental outcome that you could get if you made a measurement on a pair of entangled systems, any experimental outcome that you could get in that case could also occur if the two systems weren't entangled. So the point is that entanglement only shows up in statistical patterns that you get when you make many measurements. This is analogous to a point that we made about teleportation. Carol has no way of knowing whether Alice is actually run through the teleportation protocol or whether she's making it up. Nothing that Carol can do by way of observing her own particle will tell her the answer to that. Otherwise, we'd have signaling. And it's a deep and fundamental fact about quantum mechanics that if quantum mechanics is right, you can't use measurements on entangled systems as a way of signaling. So there's no doubt that entanglement swapping is surprising because entanglement correlations are non-classical. Whether we want to describe it as full-blown action at a distance is less clear because there's something slippery about quantum states themselves. It's a little bit hard to get a handle on what they are, and so a little bit hard to get a handle on the question of whether the apparent change in a distant system that comes about as a result of a local measurement and entanglement amounts to full-blown action at a distance. We could put it this way. Entanglement certainly gives us what we could call spooky correlations at a distance. But the question is, how do we understand spooky correlations? Causation in general is not the same as correlation. That caution still applies here, even though there's undoubtedly something going on that's different from anything that we're used to classically.